Hi everybody, thanks for watching this little video here. We're going to talk on this one about transforming and graphing simple exponential functions, okay? And by simple exponential functions, I mean things that are very basic, like y equals 2 to the x. Of course, an exponential function is a function where the variable x is the exponent. So that's 2 to the x. We could use other numbers for our base, but we're just going to keep it simple and use 2 to the x for most of this video. Okay? So the first thing we're going to talk about is a vertical shift of this graph. And so we could think of that function as 2 to the x, or just f of x, plus k, plus some number. So here's an example of y equals 2 to the x minus 3. And what I'd like you to see is that that little gold line down there is a horizontal asymptote at y equals negative 3. Okay? So take a look at that asymptote there and the connection between it and the equation. Let's look at another one. Y equals 2 to the x plus 3. And there again is our horizontal asymptote, and it is now at y equals positive 3. Okay? So we shifted it up. And what shifted actually was the horizontal asymptote for that graph. Okay. So the next thing I want to do is just kind of sum up those little ideas right there. And 2 to the x, if you have an exponential function y equals 2 to the x plus k, well, it's quite simply stated that the horizontal asymptote is just y equals k, and those two numbers there are the same. Okay, it's pretty basic, pretty obvious little conclusion there. We haven't really talked yet about the y-intercept, so I'm going to throw that idea out here at this point, and we'll come back to it later on at different parts of this video. Okay, well, let's keep going. We talked about a vertical shift here, and now what we're going to talk about is a reflection of 2 to the x. So you can see there that that graph has been reflected across the x-axis there. 2 to the x has been reflected over the x-axis, and that equation is just y equals negative 2 to the x. Okay, so that's just a flip across the x-axis. If we talked about another kind of reflection, y equals 2 to the negative x, that is actually a flip or a reflection across the y-axis. So hopefully now you're seeing that these exponential functions follow the exact same transformation rules as most of our other functions, and they do. However, exponential functions do have some interesting little quirks about them. For example, this 2 to the negative x, I could also write that as 1/2 to the x, because a negative exponent is another way of writing a reciprocal of a base. So it's actually true that any exponential function, y equals b to the negative x, can be written as y equals 1 over b to the x. So that's kind of an interesting little twist on reflecting across the y-axis. Now, let's talk about horizontal shifts, okay? These are kind of interesting, and I'm not going to make too big a deal about the graphs here, because honestly, we're going to look at horizontal shifts in another way, and I'll point that out a little later on. But it is true that a shift to the right of an exponential function is accomplished by taking your variable x and subtracting a number. Just like any other kind of function, x minus a number shifts it to the right. And I bet you can probably figure out what a shift to the left is. Yep, it's just y equals the base, in this case 2, times raised to the power of x plus a number. Okay? So horizontal shift follows that same idea, but once again, we're going to show you that the horizontal shift is actually something else, a little bit surprising. Another one of these quirks of exponential functions. But let's talk now about vertical stretches, okay? In this case, we're going to take our base of 2 and multiply it by some number, a times 2 to the x, okay? So I'll show you a couple of examples here. 5 times 2 to the x, 3 times 2 to the x, and just for comparison, this plain old y equals 2 to the x, and they're color-coded there on our graph. So you can see that 3 times 2 to the x, the green one, and 5 times 2 to the x, the red one, are a vertical stretch of the basic graph there, 2 to the x. Another thing I wanted to point out is that the y-intercepts here show up. Believe it or not, they actually show up in the equation also. So that first one, 2 to the x, the y-intercept is at 1. And we could consider a 1 to be multiplying 2 to the x. We never write it, but it's there. 3 times 2 to the x, well, the y-intercept is 3. And 5 times 2 to the x gives us a y-intercept of 5. Okay, so another interesting observation between the multiplier or the vertical stretch factor of an exponential function and how it affects the y-intercept. So let's talk about this a little bit more and kind of put it all together here. So we're going to say it in a little bit more formal way here. So let's let f of x be any exponential function of the form f of x equals a times b to the x plus k. So we have a multiplier or a stretch factor, we have b, our base, and we have k, a vertical shift number of some kind. Couple of restrictions to keep in mind here is that we cannot let a equal 0, otherwise we don't have an exponential function anymore. And a couple of things about b, we have to have b be a positive number, and b cannot equal 1. I can take b and multiply it by a negative number, that's okay, but I cannot let b actually be a negative number. Weird things happen then, be a subject for another video, I think. And we don't let b equal 1 because 1 to the power of anything is still just 1, and it's just not a useful type of exponential function. It's not that it's undefined or doesn't exist, it's just not useful in the class of exponential functions. So we don't let b equal 1. Here's the deal. You can make the assumption then, as we've said earlier, that the horizontal asymptote is y equals k. And furthermore, this thing about the y-intercept, well, it's really pretty simple, you guys. The y-intercept is simply a plus k. And that's pretty much the whole story on those exponential functions of that form. As we go through our chapter here and we learn more and more about exponential functions, there are other ways to manipulate this equation, but these are the basic ones here, the ones that you'll really need to worry about at first. But let me conclude this video here with a little final note on horizontal shift. I'm going to make the claim here that a horizontal shift is actually the same thing as a vertical stretch. Okay? That's a little bit strange, and I don't think there's another class of functions for which this is true. But let me show you how it actually is true. So observe. I'm going to make up a function here, f of x equals 3 times 2 to the x plus 4. So we've got a vertical stretch of 3, and we've got a left shift of 4 units. Okay? So it's got a vertical stretch already and a horizontal shift. Now, if I took that equation and rewrote it using a law of exponents, I could rewrite that as 3 times 2 to the x times 2 to the 4th. And I'll let you ponder which law of exponents I just used. But I assure you that that can be written that way. And just using the commutative property of multiplication, of course, I could rewrite that as 3 times 2 to the 4th times 2 to the x. And that is how we get an actual vertical stretch factor of 48 there. 3 times 2 to the 4th equals 48. And so our function now has a vertical stretch of a factor of 48. Okay? Well, I hope that video was useful. I'm glad you watched. And thanks. Be well. And now let's go do some math.